Okay, hello everyone. We're just starting the webinar. I'm going to wait a minute or two just to let some more people roll into the meeting and we will get going. I'm Walter Gordon, chair of the Niagara Frontier section. John Crucides is around somewhere. I think he turned off his camera. He's the vice chair to back me up if I lose my connection. There he is. And I'll introduce our speaker in just a moment. Upcoming webinar, our next speaker is August 24th. Another NASA person, Kurt Polzin from NASA Marshall, the chief engineer on the Draco nuclear propulsion program that they're doing with DARPA, is going to talk to us about Draco. So that's August 24th, also at 7 p.m. and those invites will go out about 2 weeks before. So far as today, ROE, as usual for our webinars, recommend you hide non-video participants. John Crucides and I are going to turn off our cameras, then you'll only see our speaker. Submit comments or technical issues via the chat, but submit questions via the Q&A tab, and we will get to them at the end of the talk. If you want to communicate with us after the talk, the email of the Niagara Frontier section is nf.aiaa, novemberfox.aiaa@gmail.com. And with that, I will introduce our speaker, Brent Cobleigh, the project manager for the X-66 at NASA Armstrong. You read all about him in the flyer, and all I've got to say is just about anything cool that flies that was at Marshall most of my career, he seemed to have worked on it. I'm very jealous. So with that, it's all yours, Brent. Thank you.
All right, thanks very much. Hopefully everybody can hear me well. Yeah, like you said, I've been out here at NASA Armstrong since 1991, and a few years at NASA Langley before that. So I've spent my whole career with NASA, and most all of that in flight tests of various kinds, both on the spacecraft, atmospheric testing, a lot of airplane stuff, and even some science work where we use airplanes to collect science data around the world. So today we're going to talk about the Sustainable Flight Demonstrator. I was kind of on working in management, above project management for a while there, but doing fun things and working on teams sucked me back in. I just couldn't, when this opportunity came up, I couldn't avoid it. Working on the next X-plane in the long historic series, and one that has such a noble goal of trying to improve sustainability of the aviation system. I couldn't stay away. So here we go. My presentation is made up of some different aspects. I pieced together some slides from a number of people, so I'm sorry if it looks a little bit disjointed at times. I'll try to walk us through that. Some of the stuff regarding Sustainable Flight Demonstrator has got some proprietary stuff that we kind of, since we just got started, we haven't been able to sort of open the aperture and get things approved. So I'm going to supplement some of the SFD stuff with some research NASA's been doing on truss-braced wing configurations in a sister project for years, including like wind tunnel testing, a lot of different analyses that kind of helped get us to the point we're at today with this project. So here we go. I wanted to just give you a quick background in case you're not familiar with NASA aeronautics. You know, it's only like between 3 and 4% of the NASA budget, but it's a critical part of that activity. There are 5 programs within NASA aeronautics. There's the Aviation Operations and Safety Program, works a lot with the FAA and with industry and airlines. There's the Advanced Air Vehicle Program, which is really where a lot of the research for new configurations, subsonic, supersonic, hypersonic, vertical lift, all of that happens. A lot of that's analyses, typical kind of engineering research analyses, wind tunnel, all kinds of predictions and design, system analysis, and all of that. And then things that kind of grow out of that and need to, when we're trying to push things to higher TRL level, they end up showing up in the Integrated Aviation Systems Program. That's where my project sits, and that is where major tests happen. Usually those are flight tests, but not necessarily have to be that. So that's where this low boom flight demonstrator is home, and that's moving into flight hopefully within the next year. I don't know exactly the date they have for that yet, but my project's there. Another project called Electrified Powertrain Flight Demo is in that program as well. And then down at the bottom, we have the transformative aeronautics concepts. This is kind of the seed corn, the low-level low TRL research, fundamental research, looking at new concepts, trying things out, working a lot with industry and universities. There's a lot of university grants in that program, opportunities for fundamental research in a lot of different areas. And then the aerospace evaluation and test capability portfolio project is really about maintaining our aerospace capabilities, like mainly the wind tunnel fleet across all the NASA centers, which are, aging. Most of them are very old, and they're expensive to operate and need to be maintained. So that's a national asset there. So quick overview there. So I work in the sort of aviation sustainability area. So what's really driven that, of course, is what we've been watching, worldwide. The climate change challenge is showing up more and more as the years go on. There is the U.S. has an aviation climate action plan, which you can find on the FAA website. It's a multi-agency plan for how to try to drive aviation carbon emissions to zero by 2050, basically. And I'm sure most of you have seen a chart like this from a lot of different people have created charts similar to what's shown here. CO2 emissions in millions of tons, over a year versus time. You can see where we were in 2019, and we had COVID. We saw a big drop in aviation travel. We've rebounded. And the projections are that if we do nothing, we don't buy any new airplanes, we don't modify, don't improve airplanes, we don't change the fuel systems that we use, that we're going to see actually a significant increase in emissions over time because of the amount of air travel is growing, worldwide. And so the goal is, how do we get to, this 0 point down here? And so there's a number of factors in that. We need to, replace the older airplanes today. That's kind of this area right here. We need to introduce new technology that can make a much bigger dent and make airplanes much more efficient. There's some operations things we can change to get a little benefit. And then you can see this big wedge down here, which is advanced fuels, sustainable aviation fuels, and maybe sometime later, things like hydrogen. And that's where a big impact is going to be. This wedge here for new aircraft technology is kind of targeting the next generation of aircraft that would arrive in the 2030s. So the wedge will grow over time, but it's necessary for a number of reasons to bring in technology in addition to improving the fuels, because there's a lot of question about whether we can actually create biofuels and things like that, whether they'll be able to get to the production rate we need to keep up with aviation. So we need to sort of simultaneously burn less fuel, and while we're trying to create more environmentally friendly fuel, and also try to keep the cost down. So burn less fuel, less cost. So that's kind of the big driver behind the project. So NASA's working both on the technology side as a primary area, on the operation side, which had a little wedge there. The alternative fuel side is really mostly driven by other government agencies and, of course, industry. The Department of Energy, Commerce, Agriculture all have roles here. We have a supporting role helping them sort of with things like measuring exhausts and seeing how these alternative fuels, what's coming out of the exhaust, things like that, helping. But our primary role is over here. In what we've created this kind of pseudo organization called the Sustainable Flight National Partnership. It's really a loose collection of all the things that we're doing that are sort of fall into the commercial aviation sustainability window. And so it's a collection of projects there is a project, not really a project office, a lead for this with some system analysis people, but in general, this is kind of a loose collection of projects that are tied together with, trying to bring a lot of different options to bear on the aviation world. And so they involve some things, and if we have any time at the end, we could potentially talk about some of these other ones, but there's a lot of work focused on gas turbine engines, making the core smaller, being able to pull more power off them to run electric motors and improve efficiency. There's some electric airplane propulsion activities, both in the sort of design field and some flight projects in this electrified powertrain flight demo. There's actually 2 flight demos that are in progress right now, are working towards flight. And then we have the sustainable aviation fuel work that I talked. And then there's some additional work on the truss-braced wing that's not in my project, that's related to some of the things that we're not going to be covering within our flight program, and I'll talk about some of those. Then it's about, okay, if we want to go to lightweight vehicles, which you really need to keep driving down, making airplanes more efficient, how do you get those composites in a way that you can build high numbers of these, like in the single aisle market where a company like Boeing or Airbus needs to build 60 to 80 or maybe even more airplanes per month? How do you get the manufacturing rate up on composites? And so that project's focused on that. There's some trajectory optimization work. And then there's my project, which is the SFD, is really, okay, we've done a lot of work on this configuration that was selected, and how do we take it to the next step and try to push the technology readiness level and solve some of these open problems, challenges we have before we get industries ready to take it to commercialization. So we'll talk about all of those, what those are and what it takes to do that. So now transitioning to the Sustainable Flight Demonstrator a little bit. So why are we doing this project? I mean, we've all seen these a huge number of advanced configurations being developed for many decades, right? Blended wing bodies, the most probably out there, but truss-braced wings been around for quite a while, and there's many others that we've worked on. And there's just a lot of challenges in trying to transition those from the drawing board to flight. And there's competitive factors. Nobody wants to be out in front, putting their company at risk. There's all kinds of technical challenges, the engineering challenges. How do you build these things? How do you integrate them? How do you make them as safe as the current generation of airplanes? And just the cost. We know it's many, many billions of dollars to take a new configuration through all the steps and through certification. So in a sense, people say, oh, you're betting the company every time you do this. And so there's some truth to that. And so how do we help industry get to the point where the risk is low enough that they're willing to take the next step and basically launch a product with one of these advanced configurations, get away from the tube and wing that's been flying, for 75 years or so. And so we launched this project to partner with industry to retire as many technical and manufacturing risks as possible, inform their decisions to help push them toward making a decision for the next generation of single aisle airplanes. That's in terms of quantity of airplanes in the commercial world, obviously single aisle is where it's at, and it's a great place to start when you're trying to improve the sustainability. And so how do we sort of encourage them to get to the point where they can take the risk and go for it, which will pull the rest of the aviation world with them. When whoever launches the first sort of more efficient airplane, the others are going to have to keep up with them. And then maximize the potential, we're going to meet the U.S. Aviation Climate Action Plan goals. So that's sort of the driver behind SFD and why we launched it. I won't spend too much time on how we got and selected the truss-braced wing. It was an open competition. There were half a dozen or so proposers that looked at a lot of different things. We were looking at something that could make it to market by 2030, so we weren't looking at the most advanced potential technology that's out there. Our focus was, hey, we need to get something out there. We need to improve what is there and continue to work the long range on hydrogen configurations and other potential configurations for commercial application, but we need to get something in there in the next generation. Every generation lasts for several decades, right? You got to recoup your costs, and so there's not going to be an airplane released in 2030 and another one in 2035. It's going to be a long time later. So we want to try to influence that as best we can. So these are the criteria that we came up with for the proposal evaluations. So we weren't just looking at the demonstrator. So the demonstrator was one piece, and that's normally where NASA would be focused. But we said, no, we want to know what your vision is for your future product. We want to know how you're going to get there. So we're less concerned right now on the demonstrator. Let's focus on what's your vision? What does this airplane do? How efficient is it? What kind of impact is it going to make? How is it going to hit the market? Is it compatible with the aviation system? What's your plan to commercialize? So that was the sort of first set of things we evaluated in the proposals that they wrote. And then how is that demonstrator aircraft going to help you get there? So we don't just want you to go play with technologies. We want you to tell us the technology gaps you have, and then put as many of those on the demonstrator as you can. So what are those technology development plans? how are you going to build the airplane? What kind of performance will you get with it? How are you going to operate, safety? Who are you going to team with, and what facilities do you need to use to get there? And then, of course, a bunch of business stuff around cost, schedule, technical risk, and those kinds of things. So those were the evaluation criteria that we used. In the end, Boeing was selected for the truss-braced wing. NASA is providing $425 million in direct payments, and Boeing is putting in over $700 million. That's the estimate now. So we were asking for the proposers to put in 50% if they were able, or more, and Boeing truly stepped up here. The 425, by the way, was the limit that we had. We said that they could propose, so that maybe they would have asked for more if they could have. And in addition to the 425, NASA is going to be moderately heavily involved in helping with this project, and I'm going to go into some of those in a minute here. But in terms of technical labor, like engineering support, analyses, and also some of our facilities for some of the testing that we're going to do. One of the most unique things about this approach that we're using is that we're using what's called a Funded Space Act agreement. It's a very unusual type of acquisition. It's not a contract, it's a legal agreement. We've never used one really in aeronautics before. The space side has used them. And it's really where you're trying to encourage something in industry that is helping either industry or helping the public or some other person. And NASA doesn't have a significant need for it. And the intention is you're trying to create a product or something that really helps, things other than NASA. In other words, we don't need this airplane to do our work long term, but we know it will have a benefit for the nation, for the public. And so this Funded Space Act basically allows us to cost share like this. NASA is not is putting in fixed, that's a fixed amount of money that we pay over different milestones. I'll show you some of the milestones later. If this cost overruns, if this runs long, we do not add more money. So there's a significant risk on the industry side. They're putting in a huge amount of money, they're carrying their risk, so there's a huge amount of incentive for them to keep things on track because it's their own money if they overrun, and it's focused on their findings, right? So everything in this proposal, it's industry-led. NASA's there to support. We did not requirements other than we have to do an airworthiness review before it flies and give them an airworthiness certificate. So there's a lot of things they need to do to satisfy that along the path. But in terms of what the requirements for the airplane are, or what processes they want to use to get there, it's kind of industry process and requirements. They're leading it, they make the decisions, and the whole idea was we want them to do the things that they need to do to get to the point where they can make a product decision, yay or nay. And so let's get the government out of the way, let's have the government help them, but not tell them how to do it. And in the end, industry will own the test airplane. Under a Funded Space Act, we can't take delivery of anything, so they will continue to own the airplane that they can use for other research if they like. Okay, so that's kind of an intro to the project. I'm going to come back to the project in a minute, but here's where I'm going to step back in time a little bit and tell you a little bit about some history. So now that we've selected truss-braced wing, we've done a huge amount of work on blended wing bodies and other configurations as well. But we've also done more recent work with truss-braced wing. It's actually not that recent, over about 2008. Some of you, if you've been to conferences, may have heard it referred to as a subsonic ultra-green aircraft research sugar. And so it's been a Boeing-NASA partnership for a number of years. And so this is sort of more of a generic truss-braced wing. These are some of the development challenges that exist. So you have this long aspect ratio, high aspect ratio wing, which means your chord is much shorter, which means your wing is much thinner. So it's a very thin wing supported by a truss. So you have many, many structural challenges in trying to design that, to optimize it, to get you, the best performance you can get. So then how do you integrate a high lift system into that? You've got an engine now that needs to be attached to a wing that has a very short wing chord compared to what you would normally see. It's basically using almost the whole chord as a structural attachment. You have some high alpha stability and control challenges with the T-tail, as we've seen in the past. Just getting everything into that thin wing is a challenge. So you got actuators, fuel, you got the structure itself. In our case, we got to also add instrumentation. So just getting all of that fit into the wing is a huge challenge. And then you've got some really unique structural joints where the truss meets the wing, where the truss meets the body and interfaces in an area that typically would be near the landing gear. You've also got, how do you design this thing that for safety in terms of a ditching or some other crash loads, things like that. Also damage, in my opinion, from ground operations, this truss. You've got interior noise challenges, because now you've got engines that are not on a low wing typical, single aisle low wing airplane. You've got propulsion system closer to the fuselage. You've got, well, hey, where do you put the fuel? You may not be able to get the missions that you want with the fuel that you can actually fit in the wing. Then you got to find other places to put the fuel. You may, with a high aspect ratio wing, depending on the market, how you want to market it to airlines and airports, you may have to put a wing fold in at some point. Which is being done now on like the 777s, obviously been done for many years on carrier airplanes. And then, how do you fit icing, de-icing systems in it? And then you've got EMI issues with having everything crammed into a small space inside the wing. And the rest of it's kind of crashworthiness. So these are just a subset of sort of things that you have to worry about and consider and reduce risk on. So over the years, like I said, from 2008, we've been working in partnerships. Some of the early phases, we're really looking at low TRL, just looking at various aspects of this configuration, trying to solve some of the obvious problems. How do you design the structure? How do you get the benefits? How do you deal with channel flow through this sharp edge here? How do you might get local supersonic flow, get a lot of drag. So you got to solve a lot of challenges there. And that was done during the early years. And through a number of wind tunnel tests, lots of CFD, a lot of other analyses that, I don't have the data to show you guys, but as we moved up, there was a strong desire to push the airplane from this kind of Mach 0.745 up to sort of where single aisles are flying today. There's a lot of marketable reasons and air traffic reasons for doing that. And that was always a challenge. How do you get this configuration with these channel flows and so forth up to higher speed? A lot of work was done there. It was very successful. So the configuration baseline is right about Mach 0.8, or 0.79, right in there. So that a lot of work was done there. And then they were looking at sort of off-nominal things like buffet, high lift, acoustics, icing, structures, a little bit more of that in some subsequent slides. But here's some high lift, ground effect testing and some icing testing that was done as well over the years. So there's a lot of different ways to analyze a truss-braced wing. You typically hear people for a moderately optimized configuration saying that the benefit for sort of a long range of the airplane is, I don't know what the low end is, but you hear like 10 or 11% at the high end. So this is NASA work here, working with Boeing. I think for this configuration, which is in our current configuration, they had it about 9% or a little less for shorter missions. Looking at it, and then there's a lot of other things obviously you can do. So this is for a high aspect ratio wing that's 19.5 relative to like 13 today. So very significant wingspan compared to the airplanes that are out there today. And then this project, I don't have all the data, looked at a lot of, what if you make the wing sort of natural or hybrid laminar flow, adding riblets, what kind of advanced structures can you do to get the weight down? How do you design these joints for lightweight and strength as well? What kind of advanced propulsion systems can you integrate? And then how do you deal with the air traffic management with this configuration? So there's a little bit more later on some of these topics, but so the aerodynamics is one piece, and then in a minute I'll talk a little bit about propulsion as well, how that might integrate. So I think some of this I already mentioned. Here's some of the things that there was a lot of interest in from NASA and from Boeing, looking at stall, buffet, icing, high lift. Since all of the performance and design kind of challenges kind of were solved, then you kind of got to look at a lot of these off-nominal situations. Here's a couple other things that were done. So we're talking about high-speed buffet testing, really looking at where do you see that. You can see these half models that were tested in the Ames 11-foot, and that's really to get the high aspect ratio up, the size of the vehicle up, and get the Reynolds number up, I should say, in the wind tunnel. one of the challenges with having something with its high aspect ratio is the wings are so long to avoid sort of wall effects in the wind tunnel. You end up having to make the model smaller, which means Reynolds numbers are smaller. So one way to gain some of that back is to do some of your testing at sort of half scale like this, or half model like this. And we've got some coming up with our projects. Or the configuration that's being developed for Sustainable Flight Demonstrator is going to have several wind tunnel tests in the same Ames 11 foot, including a full aircraft model and then a half model, just like this one is. So they looked a lot at stability and control. You can see a lot of the data on how they ran the tests back in 2022. So the bottom line is there was a lot of concern about Buffett, but it turned out that the characteristics were pretty benign. They weren't concerning, at least for the data that they've been analyzed so far. And then on the low speed side, there was a lot, how do you integrate a high lift system on something that has such high spec ratio? You've got a very long leading edge and trailing edge. So integrating all of the control systems into those is quite challenging, especially given that it's a very thin wing. So they looked at some wind tunnel tests, a couple of them actually, in looking at the performance of various high lift systems. Also looked at ground effects tests. I think this is the 14 by 22 wind tunnel at Langley, where they typically do those. And then they looked at some preliminary ice shapes that came out of some CFD results. And you can see over 500 static pressure taps on the model. So it was a pretty detailed model. And they did see that the high lift system was meeting performance goals, and the ground effect trends were as expected. And they've got some data on how to deal with what the icing effects were, at least for some of the shapes. We do expect that they will be doing some additional icing tests in the future on this configuration if it moves forward. So I do want to flip back now a little bit to the X-66. So this is our project coming back to today. So I'm going to give you a little bit more detail now. I just wanted to sort of stop there and back up and give you a little history of how we got to where we are. This proposal that Boeing put together wasn't necessarily, out of thin air. There was a lot of really good work that went into it beforehand. So they brought in a pretty strong proposal. I'll come back to the configuration here. So this is an artist's rendition of what the demonstrator would look like. So this is not a fully optimized commercial vehicle. The intent of how the X-66 will be built is to build off an existing airplane. So it's not a build from scratch airplane. So there's some compromises you make there. It is an MD-90 airplane that they're going to start with, and I'll talk about that a little bit on the next slide. But other than that, the wing is pretty close to the configuration that they like. They are optimizing around that. By the way, I don't know if you could see it in all the previous slides, but there's a little tiny surface right here that's called a jury strut as well, that over the years that they've introduced that to solve some of the structural and maybe aerodynamic problems, I'm not sure, but certainly structural challenges, and the overall system becomes more optimized with that in place. And so that is in the current design. So what do we have? We have the truss-braced wing that allows you to take the wing out to higher aspect ratios. There's always, of course, a trade-off. You can make now the wing much lighter, much thinner. It would be too flexible and too difficult to structurally maintain itself if it wasn't for the strut. But on the other hand, now you're adding additional surfaces that you got to deal with, and you have to optimize. And it's this, like everything in aviation, lots of integrated things affecting each other, and you kind of got to optimize the overall system. And so you got the ultra high aspect ratio, thin wings, strut brace. And the only thing else I want to point out here is this high wing for a single aisle airplane really does open up the trade space for the propulsion system. As we've seen, the low wings now are sort of limited on the diameters of engines they can introduce. And there are a lot of propulsion systems on the drawing boards and in development that go to higher and higher aspect ratio, higher and higher bypass ratios, or and some of those are even unducted. And the high wing gives you the opportunity to some freedom to the integration of the propulsion system, and gives you some opportunities there to really push up the overall performance. So the predictions are that when you combine the aerodynamic benefits, which, like I mentioned, were in the 10% range, with other sort of advanced technologies that we have that should be available in the 2030s, these are materials, more composites. There's a whole host of things, and you combine those with an advanced propulsion system. The predictions are that that integrated system now is pushing close to 30% reduction relative to today's state-of-the-art airplanes, like a 737 MAX. Might be slightly under 30%, but it's in that ballpark. If you listen to the aviation CEOs talking, you will hear them, at least some of them, say, we need at least a 20% benefit to really justify a launch of a new product, from scratch product. And so this vehicle configuration does fall into that and exceed that sort of minimum threshold that they think they need. And so early on, Boeing has targeted a number of key learnings. That there's a lot more detail to this that I can't show, but this kind of gives you a flavor of some of the things that they really want to learn out of this demonstrator, in addition to sort of just the overall design structure. But it's the thin wing design and integration, high lift systems, like I mentioned. How do you integrate a fuel system into this thin wing and other places? How do you deal with the aeroelasticity of this very long structure? It ends up being fairly stiff in here, but as the wingtip goes out in a very thin wing, you're going to have some flexibility there, obviously. You want to validate some of our design tools in sort of every area, aeroelastic structures and so forth. Obviously, a lot of performance measurements we want to take. We want to do a lot of long runs over, say, the ocean, so we can get some nice, clean data for them to measure the overall air performance, see if it matched predictions. Similarly, some performance for spill and control and the sort of typical flight test things. I mentioned certification, crashworthiness. How do you design and deal with that? That's not really necessarily a flight test goal, but it is certainly part of the design effort that they will learn lessons from. Propulsion system, they do obviously want to go to a sustainable aviation fuel compatibility. We probably will fly at least some of the flights with sustainable aviation fuel, but there are a few challenges there with seals and different things depending on how the fuels develop. So they want to make sure it's compatible. And then how do you deal with, again, crash type things, pylons, how they fail in various conditions, and then many structures, things which fortunately I can't go into the details at the internal structure or anything, but you can imagine that these joints are extremely significant. As the wing bends, this strut is not directly under the wing. It's actually forward of it for different reasons. So it actually puts in loads sort of fore and aft in addition to sort of bending up. And so it creates some really interesting structural challenges through that area. So that's where a lot of the learning is going to happen. So let's see, I want to talk a little bit about how we're going to build the demonstrator. I mentioned that they're starting with an MD-90. They've actually acquired 2 airplanes from Delta Airlines that were sort of recently overhauled before they were retired. From my understanding is that there are no MD-90s flying left in the world. And so they've acquired 2 airplanes. They've acquired a ridiculous amount of spares, like 38 truckloads of spares from Delta, because they didn't need their spare parts anymore. And what's nice about this, I mean, there was a whole trade study around what airplanes should we modify or build from scratch. And many airplanes were looked at. A lot of reasons why this makes sense. Some of it I'll show you here, but part of it is, Boeing bought McDonnell Douglas, so they own all the IP rights. They have all the design information. They have a lot of employees that helped build this airplane, including several people on our project, including the chief engineer, for example. So there's a lot of benefit. It has the T-tail already. So the intent is, what do we not have to do on this project? We only really care about the truss-braced wing. So let's not, if we don't have to change, this tail or anything, or the cockpit, let's not. That's the intent. So how's it going to change? So step 1 is we got to get rid of the wings, and the engines are no longer going to be on the fuselage. They're going to be under the wings. So those got to go away. And it turns out to get the configuration they're really looking for, you need to shorten this thing too. The MD-90 is an extremely stretched airplane, so they're going to take 19 frames out. which this airplane being a sort of older airplane, it's actually less difficult to do than you might expect. I've seen it's really drilling out lots of rivets and taking things apart and putting them back together. It's of course extremely challenging and precise work, but nevertheless, it's they don't have to take a saw out and cut the airplane open. There are ways to do this. So that's going to go away, and then this is what the ultimate airplane is going to look like. It's going to be replaced. So you can see the engines aren't there; they're up on the wing now. We have a much higher. I mean, for the same sort of fuselage diameter, you're ending up with extremely long wings relative to that. And this picture really shows off where the truss comes in, right? The truss is kind of perpendicular to the fuselage, comes into the area where the landing gear were, and there's some offset here, which you can kind of figure out on your own how that helps aerodynamically. So that's basically, I mean, obviously I'm super simplifying things, but nevertheless, that's how we're going to transform this MD-90 into the X-66. The engines will be a modern turbofan engine. We're not developing a new propulsion system, but we'll be able to have something that's sort of comparable to the state of the art. And then, of course, you can always do trade studies beyond that to look at other propulsion options. I did mention earlier that Boeing will retain ownership of this airplane. So at the conclusion of our flight test, which is intended to be about a year, and we're targeting like 2028, 2029, that they can use it for other things. Obviously, they can integrate other technologies, use it as a demonstrator for other things. We will be doing a lot of instrumentation on this. This is all going to be built here in Palmdale at Boeing's facility, which is only about 30 or 40 miles from Edwards Air Force Base, where I work at NASA Armstrong. So once the airplane is built, they will fly it. On the first flight, the intention is to bring it here to NASA Armstrong and then do all the flight tests from here, which provides them lots of restricted airspace and access to the coastal areas where there's a nice clean airflow for performance testing. So what is NASA doing here? I've been talking mostly about what Boeing's doing, but NASA does have some significant roles here. We are going to help them with wind tunnel testing, which I did talk about. We will have one of the simulations that will be doing all kinds of work, some of it preparing for flight, emergency procedures, training pilots. But my guess is they'll be doing design analysis work and other things as well. Structural testing, we're going to test the actual truss in our loads lab, and we will send teams over to help Boeing with the structural test over the entire wing over in the facility in Palmdale, like I said, which is 40 minutes away or so driving. So we'll be helping with that. We're going to do all the flight tests here, so control rooms, hangar, radars, data management, all of that, chase aircraft. That'll all be here at Armstrong. And then we have acoustic arrays that we'll bring out for some of the flight tests. And then another big piece of that is we're actually going to have engineers working, or we already do have engineers working on their integrated product team. So this is where we're bringing in structure experts or discipline experts to help them. And we might have some unique knowledge in some areas, and sometimes it'll just be being another person to help on the team, right? But we'll be outnumbered by 5 or more to 1. But I think it's valuable that we can bring some our lessons learned to help with the overall activity. So it is a joint partnership, but led by the partner, as I said. So this is the timeline, and I don't know how well this comes across, but I know somebody would want to know what's going on with the schedule. So we awarded this back in January. We've already gotten through 2 of the milestones. So these are the milestones I mentioned, the $425 million that NASA's putting in. We pay Boeing when they achieve milestones. So each one of these has a dollar value associated with it. And as we go through it and they meet the criteria for that completing that milestone, then they will get paid that, whatever that amount is. So we've been through a kickoff and we call airworthiness. Airworthiness is basically agreeing on how we're going to do the airworthiness and work together and do life cycle reviews and work jointly on a lot of stuff. So it's a whole bunch of how we're going to work together through the life cycle. That was very successfully completed. The conceptual design review, which is at a pretty high level of sort of the requirements to get through it are pretty high. They're sort of at the commercial level of a conceptual design review. That's going to be out in September. and then the requirements review out in December. We slipped it a little bit to sort of raise the bar on what we wanted to accomplish in that review, so that's why they're out there now. The MD-90 is actually going to be flying very soon here, like next month. It's in a storage facility. They've gotten it through all the maintenance, and they're going to be moving it down here to Palmdale, likely next month. So that'll be actually ahead of schedule. And then like PDRs out in these are fiscal years, which is September to September. So this is actually calendar year 24. PDR will happen. You can see CDR out here in 26, leading through lots of integration and testing and structural testing until we get out to first flight, which they have out in September of 2028. And finishing, like I said, about a year later, flight tests like 10 months and then close out. So that's the project. And again, these dates, there's a lot of pressure to keep these dates because I mentioned the new product introduction is expected, desired in the 2030s. Once you decide to build it, it takes a number of years, obviously, to design the full-scale commercial airplane if they do decide to do it, and then they have to go through certification, which is no small feat. So let's see, I think that's what I had for SFD overview. Like I said, I do have a few slides on some of those other related sustainability projects that we could touch on if like. I think it's a good time to stop and talk about whatever people would like to ask.
Okay. That was terrific. Thank you. I like to think I have a good handle on different aspects of design. So many things I hadn't even considered that you got to cover here. Two questions, well, several actually. One is the total value of NASA's labor and facility contributions fixed or variable under the FSAA?
It's sort of variable. The content of the testing has been fixed ahead of time, so we know what we've agreed to do. If it costs us a little bit more to do it than we expected, we will cover that. And then we've kind of scaled the amount of workforce that we've offered up. So during the life cycle, there's kind of a dollar figure associated with how much money we can, use. And if Boeing comes back and says, hey, we'd really like some help in this area and we don't need as much help in this area, we can make those adjustments. So there's not a lot of cost risk until you get to the end. So if for some reason the program slips a year, then we will have some risk that we'll have to support our own workforce for an extra year, but we are sort of budgeting in case things like that happen, or at least trying to budget. It's hard to budget that far out, but we do have plans for that. So we expect to have a peak staffing in the 25, 26 timeframe that actually during flight tests, it's, up in the 60 to 80 NASA people total. And Boeing, will have significantly more than that.
Okay. We have another one. Does the A in X-66A mean anything? Do you think there's going to be a follow-on, a B?
Yeah, it's actually, we get that a lot because it's unusual, a little bit unusual. It turns out that the Air Force for quite a number of years now, I don't know how long, but maybe a decade, they've been assigning these extra letters to everything. And the intent is if you make a major modification at some point, the letter would trigger just like it does for, F-16, CD, F-18EF, all of that. Those letters increment when there's a major change done. So rather than waiting until that happens, they actually assign you the A to start with. A lot of people, when they're talking about X-planes, like X-59, our low boom airplane, is actually X-59A, but they just drop it. And so we're using it right now. My guess is we'll just start calling it X-66 after a while. But like I said, Boeing will own the airplane. If they want to go put some crazy advanced propulsion system on it, modify it for hydrogen, I don't know, anything like that, they potentially could do that and basically get it reclassified as X-66B, that version.
Okay. One here. What was in it for Delta? Do they have any equity in the program? Was the stuff purchased from them, Delta Airlines, the MD-90s?
Yeah, there's a weird thing that happened. I guess Delta and Boeing, they have a relationship, obviously, and money's changing hands. I guess there was some kind of not disagreement, but like somebody owed somebody something, and this kind of worked into the deal. It's kind of like a bartering agreement on a big chunk of work was kind of a bartering thing. So they ended up, I think, mostly giving. Maybe Boeing paid some money for some of it. I don't know, and gave them a lot of parts. So no, they're not financially or actively involved from that perspective. However, there is expectation that we're going to have an airline consort advisory group. We've kind of met with them already once. If Boeing's working with them to kind of sign some agreements that they could come on as advisors. There may be an announcement about that soon. But there's a number of airlines that would be sort of advising the development of this airplane over a long period of time, and it's kind of the big airplanes US-based airlines that you might expect. So there's several of those, and Delta's one of them.
Here's one that I thought of earlier and then forgot, but it just came in. Are the truss braces considered lifting surfaces?
Yeah, they in some conditions, I believe that they do have some lift. It's not a major driver of why they're there, but once you decide they have to be there, of course, the driver for any designer is, well, how can we use them, or at least reduce the penalty of them being there? So obviously, they're going to have some skin friction and other things. So the goal is to avoid things, bad things, and if you can also get some good things out of them, that's great. But I think the answer is there are some performance benefits, at least at some flight conditions, but I actually don't know the details that well. But I'd say it's a huge part of the design in terms of, when the CFDT guys are working, they're making tiny little tweaks in it here and there to really optimize things, and that's really why it probably took some time to get this configuration matured to the point where we can fly it at Mach 0.8 and feel comfortable in the performance benefits.
Okay. Can you touch on the objectives of the acoustic testing in a little more detail?
So it was never really, and it wasn't, as part of the proposal, we didn't actually give any proposers a benefit or like extra points for having a lower noise configuration, because we wanted them to focus on the sustainable, reduce emissions. So all we said was your configuration has to be able to meet the certification agency rules in the time period that we're talking about, 2030. So there's not anything specific we're trying to validate, but with these phased array acoustic arrays, and actually I did some testing on my previous job recently, about 5 years ago, on landing gear noise, and we put out this array that's like, I don't know, 200, I'm not going to say yards, that wouldn't be fair to you guys, like 200-300 meters around with several hundred microphones on the ground. And with that, you can actually pinpoint the noise sources, not just what is the overall noise on the ground like you would do for certification, but where's the noise coming from? And we were able to see noise from like fuel vents, and at the flap edges, we could actually pinpoint where the major noise sources were. So I think that that's the intent, is to look and basically learn, like find out what we don't know, right? Where the noise is coming from. Our flap system may not be a full production design, so what can we learn about it to improve the final design? Is there anything funny going on with the truss wing interface? So I think it's to learn, and I haven't seen more than that. As we get into this, I'm sure that they'll start better defining some of the objectives for that, but that's kind of what I suspect.
Okay. Is the wing construction going to be primarily composite? And if so, is there a plan to integrate sensors into the composites?
So I probably can't talk too much about the design, and I don't know enough to probably answer the question well. You can expect there's going to be a lot of composites and lightweight materials. The instrumentation piece is still a little bit TBD. It's going to depend a little bit on what we want to get out of certain things. We are looking at some advanced instrumentation to learn certain things about bending and stresses. We have fiber optic shape sensing systems here at NASA Armstrong and also at NASA Langley that are very highly advanced and use fiber optics to get very precise measurements at very short distances apart for very simply just by gluing down this hair-like fiber. And you can actually integrate that to get wing shapes and in some cases, I think, measure temperature with them even. And so I think there's a lot of things you can do, but I don't think we've figured out exactly how to combine sort of regular instrumentation with some advanced instrumentation to learn what we want to learn. But we've got, like we're not flying until PDRs in a year and a half or whatever it is. So we have time to figure that out here.
We're getting lots of good questions. Here's one in early trades for the configuration of the aircraft. Was a low wing considered with the truss coming down from above and retain the rear engine configuration?
Oh, I don't know about the rear engine, and I don't know much about the inverse truss-braced wing. I did ask, somebody asked that question in my presence not too long ago, and one of the designers explained why that didn't make sense. And it's escaping me why that was. There were some pretty good reasons why that was, but I don't unfortunately remember what that was.
Here's one. You mentioned that the truss braces induce a level of twist to the outboard section of the wing. Is there any consideration for that being studied to enhance or replace ailerons?
Sorry, say it again, Walt.
You said the outboard section of the wing, outboard of the strut, will have some twist, just aerodynamic twist as it's flying. Has someone considered taking advantage of that twist to augment or replace the ailerons? Essentially, wing work on the outer wing. Okay,
I have not heard that mentioned before, and I think trying to roll the airplane, at least at cruise for sure, at with a wing like this is probably not how they would use. They probably wouldn't use the outboard ailerons, my guess. They probably use inboard flaps to do that, where it's a little stiffer anyway. But I don't know the integration challenge there. I'll be with the guy that knows, though. If you're going to be at Oshkosh next week, the chief designer for this airplane, they call him Chief Architect Eric Johnson, will be there. And you can try to get that out of him, although I'm not sure how much he can share.
Yeah. One here, can this be a scalable design for bigger airplane?
So Boeing, when we did the award, Boeing released an image that shows that there's a potential to family this airplane in a different way than normally do. So if you talk to somebody who works in the commercial world, they will tell you there is no you don't build an airplane, you build a family of airplanes, and because the airlines want different sizes and different passenger loads and all of that. So if you don't have a family, your product's going to be doomed. But every time you get off nominal from the original optimized design, you're paying a little penalty for stretching the fuselage to get more people in. Sometimes you design for that in the optimizations in the middle somewhere, but nevertheless, there may be more sensitivity to this, I'm not sure, but they have looked at having two airplane sizes. Maybe the fuselage and cockpit and a lot of things are similar, but the wingspan is different. Whether you fold wings or not might be different. Which gate you go to might be different. To sort of span a bigger range of passengers. So that's still being studied. It's certainly not, they haven't nailed down what their production vehicle would be, so it's hard to know. If you start going to bigger vehicles, it's possible, physics says it's possible, but I don't know if the airports would like it, right? So when you scale up, the wingspan may be so incredible that that's a challenge. So I don't know how well it scales to sort of, dual aisle airplanes or wide bodies. The other thing to think about, at least for today, you can still see my my laser here. There's an FAA rule about if you do fold a wing, that you have to there's a couple of things about there becomes an ITAR issue for certain things beyond the wing fold, and I think it might be like hydraulics or power or something. If it goes beyond the wing fold, it becomes an ITAR thing, because then it's like a military landing on carriers. You're helping people figure out how to build military capabilities. So there's the ITAR issue, and then there's another FAA issue, or FAA certification criteria, as I understand it. It says for certification, if you have a folding wing, you have to be able to show, not prove in flight, but show somehow through analyses that you can lose one of those wingtips at the fold and still land the airplane safely. So if you go to a full-scale airplane and you're trying to fold it to fit into sort of standard gates, the fold might be way more inboard, in which case it would be, you know, way more challenging to try to safely land the airplane if you did lose that. So I don't know. Maybe there's workarounds. Maybe you can change the rules. You know, there's a lot, but I don't know. I'm totally speculating here. So.
Okay. At the beginning of that answer, you started talking about optimization and deviating from nominal. Not really a piggyback, but where did the 19.5 aspect ratio come from?
Well, I mean, I think it's, you know, it's not fully decided where you go with this thing. There's just a lot of trades going there between the size of the size of the wing, how you build it, the flexibility, how it ties in with the truss. You can keep pushing the wingspan, but are you losing benefit at some point? Because now you're looking at your wingtip and your wing chord is getting so small out there. I think there's a lot of things that trade into that, and then of course it's fitting into the gates, right? So ultimately, the thing has to fit into the aviation system. So some airports will be okay with providing more space. Others may need you to fold it, and so there's that challenge. So I don't know the exact reason on why, you know, this particular aspect ratio is, you know, kind of where the desire is right now, but and the production vehicle may be a little bit different. It might be a little bit less or a little bit more.
Here's one. Exciting to see the truss-braced wing moving forward, as this was my first PhD project. Is there still any opportunity for universities to get involved with the project?
That's a good question. So hadn't really thought about that. We have a lot of proprietary issues, as I mentioned. When you're working with a company that's putting in the vast majority of the money, we've basically given up most of the control. So it's kind of up to the partner to decide who they want to bring in. Now they do, I've been to their facilities and they're staffing up very quickly, and they have a lot of spaces for students, even at the high school level. So I know that they have interns to come work. But in terms of research done by universities, I'm not sure. I'm not sure if they have anything there or not. Our project, the Advanced Air Transport Technology Project, AETT, that was on some of the slides earlier, that work that they're doing is on a generic truss brace wing. It's not the Boeing design. And so that a lot of that work is publishable. And there may be some grants and things that they do. I don't know. Also under that university project I mentioned, University Leadership Initiative, it's called, they also take pretty significant proposals from industry or from universities to do advanced work, multi-year advanced work. So I'm not sure exactly how that works, but I'm sure you can find it online.
Okay, another one. How finalized is the strut attachment point?
I feel like that they're getting to the point where they've got a concept, structural concept. They're close to having a concept that they're happy with. And it was only because we've increased sort of some of the things that they wanted to get done before we did the conceptual design review that we slipped it from July to September. So the intent was we were going to do the conceptual design review, you know, now, and so the overall design is in really good shape. Not that it won't change more. I mean, we're not at PDR yet, but in terms of the basic design, it's pretty far along.
This might be the last question. Are there any programs a little further out for 2035, 45 timeframe entry into service for hydrogen fuel cells or hybrid electric?
Mm-hmm. So a couple things. So one is our electrified powertrain flight demo project is a flight program that is retrofitting airplanes with electric motors. So there's two awards that are two teams working. One is a General Electric team, and one's a just forgot the name. I'll think of it in a second. Less well known, but very good company. So that project is trying to demonstrate an integrated powertrain or hybrid kind of configuration on a moderate sized airplane, like a commuter sized airplane or a little bit smaller. So that's happening. There are, through these other projects, a lot of studies ongoing looking at boundary layer ingestion, advanced propulsion, and definitely looking at hydrogen configurations. That's looking out in the next generation. So this whole Sustainable Flight National Partnership is really trying to focus on the 2030s. How do we get the best propulsion system, the best aerodynamic configuration, all advanced, materials and processes and manufacturing to sort of coalesce into that 2030s next generation of airplanes, and then in parallel be working the long range sort of seed corn advanced configurations as well. Those are going to be critical behind, and it may be that the large airplane we were talking about earlier, what's the the jumbo aircraft propulsion system, it might be hydrogen or some hybrid thing. And this airplane could be hybrid too in terms of electric. I mean, that could be an option for this too. I think saying hydrogen for this airplane might be challenging just because there's not a lot of excess volume, but certainly electric's an element that could be introduced here.
Okay. That seems to be it. Did you want to cover the other concepts that you alluded to earlier, or what was your plan?
If people have time, I'm happy to do a little bit.
I think people are free to go anytime, and I'm sure some people are interested. So if you have a little time, please do.
Okay, it's just like 3 or 4 charts, but I mentioned these other projects that in addition to the one that we talked through this briefing, and I'm not super familiar with these, by the way, but they all have a slide that looks like this that gives you a little bit about what it is. So there's a whole project team focused on this, and most of these are integrated with some industry partner or sometimes multiple partners. But this is looking at compressing, the core, making a smaller core that's more efficient and also is able to pull like 20% power extraction. So to be able to help hybridize an airplane where you have one propulsion system maybe, and then the other propulsion system, if there is one, is powered, is an electric system. So it just, provides some integrated benefits, just like we do with, hybrid cars. So that's one project, and it looks like, so they've made contract awards in 2021, and there's proposal, let's see. Phase 1 was some stuff that they did in 2021, some studies, and then they put out the proposals, and they've received those in May. So I don't remember if I've heard that they were awarded, but they probably have, or probably getting close to award on those if they haven't. And then the next one was looking at electrified aircraft. So this is not the flight program I was mentioning earlier. This is just looking at all the issues mostly through ground test and advanced development. So there's a lot of smaller contracts looking at the various elements within an electrified system, inverters and power conversions and battery systems, and if needed, generators, making them more efficient, dealing with heat and just, heat exchanges across the system, how to get the weight down, and getting reliability up obviously is key. So there's a number of investments here. These are sort of lots of individual investments across the whole portfolio, and I definitely don't have the details on all of those, but it's probably a lot of that can be found up online. So the EAP project, you can go look up. And then I mentioned EPFD. So it's magniX is the other company that's modifying one of the propulsion systems. Or maybe it's two on one side, but they and then the GE on the other ones. They're putting a single electric propulsion system and looking at the integration. So these are all about the learning too. It's not just about, hey, do it and fly it. It's about what does it take to do it? How does it affect the other systems? How difficult are things like EMI is always an issue, especially when you're talking high power. How do you design things for high altitude and not get arcing? And the thing about taking things to flight is it forces you to think through all the issues. If you just do a ground test, you can take shortcuts, and even if you don't think you are, I promise you are. Because as soon as you say we're going to fly this eventually, you're wearing your airworthiness hat all the time going, how are we going to get this through certification? Is it really going to pass altitude? Is it really going to pass all these ground tests? Can it survive? We have a pilot's life on the line now. It changes the whole dynamic. And so having an integrated flight program really is the graduation exercise, and is really the learning tool these companies need to take it to the next step.
I have a question on that one. If you just want to flip, yeah, there you go. You say baseline unmodified flight testing of GE Saab 340 was conducted. What was the purpose of unmodified flight testing?
I think it's to look at probably to get a baseline on performance. And like I said, I'm not that familiar with it, but they probably tried to measure, drag and performance, and then wanted to compare that against, once they modify it with the electric system, how much benefit they get.
Okay, no, I'm just curious then.
Yeah, with the same kind of instrumentation system. So you have a real apples to apples. If you're comparing against, the manufacturer says this is the performance, and we compare it against what we measure, you never know, are those really apples to apples? So we're using our instrumentation system, the exact same flight points, same flight, same pilots, everything. Now you got a really apples to apples, and you can take that delta really well. And also make sure that the airplane is, good. Some of these airplanes came out of long storage. I think we got at least one of them for free. So, so then there's this high rate composites. How do you get the production rate up by, a factor of 4 to 6 over today without cost or weight penalties? So exploring all kinds of advanced manufacturing techniques and different materials, thermosets, thermoplastics, and looking how to do things out of autoclave if possible, automatic, fiber placement machines, and how to do those in a way that you can keep up the manufacturing rate. Because for anybody that's been out to see like the 737 line, it's impressive when you see these train cars come in from Kansas with these 737 fuselages, and they're pumping, 2 airplanes out of the factory every day. It's incredible to watch how quickly these things get integrated, and you got to have just a high production rate to be able to handle that. So, I mean, this team's saying the state of art right now is, maybe you could develop 10 to 15 composite fuselages a month, and they're trying to get it. How can we get it up to 80 to 100 without having massive infrastructure increases over today? Because we were doing it with metals today. I mean, that's the 737 is an aluminum, I believe, alloy that's easier to manufacture at high rate. So I think that was it. Just thought maybe you'd see a flavor of some of those other things. So these are really tangible. I mean, because this is near term, 2030s, putting a lot of money into some really practical, tangible activities that have high industry connection. And it's so, well, we're still looking, like I said, at 2040s hydrogen. We can look at CFD and system analyses that we don't need to spend it's not as expensive to do. We don't need as many people to help us. We can try different things and fail, do some wind tunnel testing, try and fail. But when you're putting huge dollars into these things, you really want to bring in people that know what they're doing and have strong proposals and are ready to move forward. So that's what these major activities are for.
No, this was fascinating. Thank you for the extra slides as well. This one in particular, just looking at the 60 versus 10 or 15 for the composites. Those are pretty fascinating stuff.
And this is the case where we've got, and we've done this with other projects, where you have a huge industry teams. So these are competitors that are coming together and working on various elements of this problem and sharing at least some of the data with each other. So it's a very challenging thing to put together these cooperative research teams, but it's, you know, it's Boeing with Spirit and, major Raytheon and, all these big companies that are building various components. And in some cases, they don't overlap what they do, but they're trying to learn from each other, and they each put in their own money too. All of these activities I'm talking about are, at least on this project, are cost share with industry. And in most cases, at least 50%. So it's not just them trying to suck the government money out. It's them putting their own money in because they see the value.
Mhm. Mhm. Okay, well, I think that'll probably wrap it up.
Yeah, thanks.
Okay, everyone out there, I hope you appreciated it. Brent, really, really appreciate your time. Just fascinating, all the aspects that we wouldn't normally have considered.
Thanks. Yeah, well, thanks for the opportunity.
Okay, and take care, everybody, and we'll see you. What did I say the next one was? August 24th, Kurt Polson. Keep your eye open in your email for that. Okay. Good night, everybody. Thanks again, Brent.
Okay, bye-bye.
Bye-bye.